What NASA isn't telling us about Betelgeuse. Your grandparents missed it. Will we see the supernova? How Betelgeuse could become Earth's second moon. Hey, truth seekers, today we're connecting dots between Betelgeuse's weird behavior and, well, you decide. One of the closest massive stars to the sun is acting weird. Betelgeuse recently dimmed down to just 1/3 of its usual brightness. What could be causing this strange behavior? Could this mean it's about to blow? Grab a cup of coffee or a soda if that's your thing, and settle in, because today we're diving deep into everything going on with the mysterious Betelgeuse. Betelgeuse. Look toward the Orion constellation and you'll spot this infamous star at the shoulder of the mythical hunter, also known as Alpha Orionis. It's usually easy to find since it's the 10th brightest star in the sky. Well, usually. But over the past few months, astronomers have noticed something off about this star. Right now, it's only about 1/3 as bright as normal, enough that you can see the difference with the naked eye. In fact, it's dropped all the way down to the 24th brightest star. To figure out what's going on, we've got to talk about what makes Betelgeuse special. Because this isn't just any ordinary star. No way. For starters, it's way younger than our sun. While the sun formed from the collapse of an ancient giant molecular cloud roughly 4.6 billion years ago, Betelgeuse was probably born just 10 million years ago. For perspective, that's around the time our early human ancestors started branching off from what would eventually become gorillas. If we scaled the sun's age to a 365-day calendar, Betelgeuse would have been born on December 31st at 5 a.m. It's so ridiculously young that rocky planets like Earth probably wouldn't have had time to form yet, and honestly, they never will. So yeah, Betelgeuse is a baby in star terms. But in another sense, it's already old, at least compared to how long it's expected to live. Let's compare it to the sun. Our sun is basically middle-aged, with enough fuel to keep burning for another 5 billion years before it balloons into a short-lived giant phase and finally fizzles out as a dead white dwarf. Betelgeuse? It's running on fumes. It's already in its giant phase. See, this star has been hogging resources its whole short life. It started out with a crazy 15 times the mass of our sun, and ever since, it's been burning through its fuel like there's no tomorrow. This star is an absolute monster. It blasts out 100,000 times more energy than our sun. And even before it became a giant, like it is now, back when it was in its main sequence phase, where our sun currently sits, it was still pumping out tens of thousands of times more power than our little star. You've probably heard the saying, the candle that burns twice as bright burns half as long. Well, in this case, we'd say, the star that burns 10,000 times as bright lasts 1,000 times less long. Though to be fair, Betelgeuse started with at least 10 times as much candle wax to begin with. Massive stars like Betelgeuse are super rare. Just like in the animal kingdom, most stars end up a pretty average size for their kind. But every once in a while you get some freakish set of circumstances that spit out a giant. And these giants stand out. Betelgeuse is one of those freaks. Only 1 in 200 stars is born with as much mass as this beast. And not only is Betelgeuse massive, the fact that it's entered its giant phase means it's also freakishly huge. To wrap your head around just how big we're talking, let's break down what's going on inside a star. Stars have two main zones: the core, where fusion happens; the envelope, basically just a bunch of hot gas sitting on top; As stars fuse hydrogen into denser helium in their cores, they build up an inert helium ash at their centers. Since helium is denser than hydrogen, the core shrinks, which makes it heat up even more. Eventually, the temperature and pressure get so extreme that helium starts fusing into carbon via the triple alpha process. This dramatically boosts the core's energy output, which then makes the outer hydrogen envelope puff up, like a hot air balloon. Except in this case, the balloon has expanded to the size of Jupiter's entire orbit around the Sun. Yeah, it's that big. That's basically what's happening inside Betelgeuse right now. Why it's the colossal beast we see today. But it won't stay like this forever. Because now, as it keeps piling up carbon ash in its core, the temperature and pressure keep climbing. Eventually, even carbon and heavier elements will start fusing. And once that happens, game over for Betelgeuse. We're looking at a few hundred years, maybe a couple thousand, until its demise. What happens to massive stars like Betelgeuse when they die? There are two likely possibilities. The one you're probably hearing most about is a supernova. Remember that the core will eventually start fusing carbon and even heavier elements in its center. But once it starts producing iron ash, that's game over. That's because fusing elements heavier than iron is what we'd call an energy drain, meaning you actually have to put in more energy to make the reaction happen than you get out. This reaction sucks energy from the core. Remember, this is a massive star with huge gravity trying to collapse it inward. When the heat source weakens due to this iron ash buildup, there's nothing left to resist gravity's pull, so the star completely collapses inward. At this point, Betelgeuse has two possible futures. One goes out with a bang, the other with a whimper. As the star's outer layers fall inward toward the core, one of two things happens. Either the core resists this inward collapse and bounces back, or the core can't resist and gets crushed. Stars at the lighter end of the massive spectrum, around 10 times the Sun's mass, won't create enough pressure to fully collapse the core. Instead, they compress it into an ultra-dense neutron star that bounces back. This rebound creates a massive shock wave that blasts outward, releasing incredible energy and spewing matter into space, what we call a supernova, or more technically a core collapse supernova. But if the star is heavier than 10 solar masses, now there's so much material falling inward that it overwhelms even neutron matter's resistance. The star collapses all the way down to a single point of infinite density, a black hole. Sometimes there's a partial bounce that forms a neutron star first, but then more material falls back and tips it over into a black hole. Other times there's no bounce at all. The star just implodes and disappears without any explosion. This silent disappearance has actually been observed before. Around 2010, astronomers saw another red supergiant in galaxy NGC 6946 simply vanish. This wasn't even noticed at the time. Only later, when researchers at a state university checked archival data, did they find this remarkable event. That star probably started with about 25 times the Sun's mass. Meanwhile, lower mass red supergiants in the 10 to 15 solar mass range have been seen to explode. When we compare these observations to theoretical models, they match up pretty well. The models predict whether a star will silently collapse into a black hole or go supernova based mainly on its mass, but there's some randomness involved, Factors like rotation speed, metal content, and the chaotic nature of a star's interior mean we can't always predict exactly what will happen. We can't say for sure what will happen based just on a star's mass. That's part of why it's so hard to predict exactly what's in store for Betelgeuse. The situation gets even trickier because we don't actually know Betelgeuse's current mass, let alone what it weighed when it was born. And that's because we don't even have an exact distance measurement for the star. This leaves us with a huge margin of error when estimating its mass. Looking at theoretical models, it's definitely possible Betelgeuse might one day just vanish without any explosion. Now that we've covered this background about massive stars, let's finally talk about what's been going on with Betelgeuse these past few months. First thing to know, Betelgeuse is a variable star. Its brightness changes naturally. It's not some steady light bulb. We've seen its brightness fluctuate by a few percent, sometimes even 10% for decades. What's really unusual about the recent changes is that we're seeing a steady, steep decline in brightness that's dropped all the way down to 1/3 of its normal level. That's seriously weird behavior. I should clarify that 1/3 brightness was the lowest point in the star's recent dimming episode. In the last couple weeks, it's actually started stabilizing and even brightening back up a bit. Things get even more interesting when we look at these two images taken about a year apart. Normally, we can't get clear pictures of individual stars, but supergiants like Betelgeuse are so huge we can at least get these fuzzy images. The difference between these two photos is obvious, and combined with the dimming, it's got a lot of people concerned. So let's address the question everyone's asking. Does this dimming mean Betelgeuse is about to go supernova? Short answer, probably not. Here's why. First, we don't have any solid evidence that stars dim significantly before going supernova. The physics inside these stars is incredibly complex, with gravity waves and other factors affecting their brightness in unpredictable ways. Here's an example from Professor Jim Fuller showing predictions for a star's brightness versus surface temperature in its final years. The brightness isn't just dimming, it's all over the place, sometimes getting brighter too. The truth is, we've never actually observed a star in the days or years before it went supernova. So we don't have any real-world data about how stars behave right before they explode. These models are the best information we've got right now, and frankly, we just don't know how stars act in their final moments. Here's the thing. We don't actually know if what's happening now matches those model predictions. That graph I showed you displayed luminosity, but here's the catch. The recent dimming everyone's talking about doesn't necessarily mean the star's total energy output has decreased. All these reports about Betelgeuse getting dimmer are based on visible light observations. But stars like Betelgeuse emit radiation across the entire electromagnetic spectrum. To calculate true luminosity, we'd need to add up all that brightness across every wavelength, and that's not what these dimming measurements show. Fortunately, astronomers have a way around this. By observing other parts of the spectrum, like infrared, we can get the full picture. Just last week, infrared measurements from the O'Brien Observatory in Minnesota showed Betelgeuse's infrared brightness hasn't changed from what it was 50 years ago. This means the dimming we're seeing is only happening in visible light. The star's total power output remains steady. So maybe we can relax a bit about imminent supernova fears. But that still leaves us with two big questions. Why the visible light dimming, and what's up with that lopsided appearance? There are two leading theories. if we rule out the supernova idea for now. First up, giant star spots. We see small sunspots on our sun all the time, areas where tangled magnetic fields block heat from reaching the surface, making those spots cooler and darker. It's like when you pull a piece of iron from a fire. It glows red hot at first, then cools and darkens. For Betelgeuse to dim this much from spots, about 2/3 of the visible surface would need to be covered. If the far side is spot-free, that means roughly 1/3 of the entire star would need spots. Our sun never gets anywhere near this level of coverage. At peak activity, only about 1% of its surface has spots, causing just a tiny 0.07% brightness change. But other giant stars have shown much larger spot coverage. The orange giant HD 12545 in Triangulum, for example, was found with spots covering about 1/4 of its surface. Not quite 1/3, but close enough to show this is possible. Sunspots come and go on an 11-year cycle, and stellar brightness is generally pretty stable despite spot activity. When we put all this together, the spot theory could explain both why Betelgeuse's total luminosity isn't changing much and why we're seeing this visible light dimming. This star spot theory could also explain that lopsided image we saw, all with one neat explanation. On our sun, we know spots form when magnetic fields mess with heat circulation. These spots are typically about Earth-sized, but if we look closer, there's another layer to this. You can see a finer-grained pattern. Each of these little cells is roughly the size of Texas. What's wild is this isn't computer-generated. It's actual data from the Swedish Solar Telescope showing our sun's surface in incredible detail. Each bubble you see is the top of a convection cell, what scientists call a granule. This shimmering effect is called granulation, caused by hot plasma churning beneath the surface like a giant lava lamp. The size of these granules depends directly on a star's surface gravity. For our sun, with surface gravity about 28 times Earth's, we get Texas-sized granules. But Betelgeuse? Its gravity is pathetically weak, about 3,000 times weaker than what we feel on Earth. So naturally, its convection cells are absolutely massive. Betelgeuse doesn't do anything small. Some stunning computer simulations show just how violently this star's outer layers bubble and churn. Unfortunately, our telescopes can't see Betelgeuse's surface that clearly. If we adjust the simulation to match our actual observational limits, you can still see how these giant convection cells could create both dark surface patches and that lopsided appearance in single images. So honestly, this extreme but completely natural convection activity might explain everything we're seeing with Betelgeuse right now. But I did promise 2 theories, and the second one's just as interesting. Remember how weak Betelgeuse's surface gravity is? It makes you wonder, if you were standing there, could you just jump right off into space? The math says yes. Escape velocity from Betelgeuse is only about 60 kilometers per second, compared to the sun's 600 kilometers per second. This opens up another possibility. A massive convulsion inside the star could have blasted material right off the surface. That ejected material would cool as it traveled outward, eventually forming dust that now partially blocks our view. Basically, Betelgeuse might have coughed up a cosmic dust cloud that's making it look dimmer. We've even seen previous dust releases in actual images like this one. With the giant star spot theory, the surface actually cools slightly. But with the dust theory, the surface stays the same temperature. We're just seeing dust blocking our view. Astronomer Emily Levesque recently studied Betelgeuse's surface temperature using spectral analysis. Her team found the star's temperature doesn't match what we'd expect from major cooling, so they're leaning toward the dust explanation. This gives us two solid theories that don't require a supernova. Of course, since we know so little about stars' final years, we can't completely rule out that this might be pre-supernova activity. But stars typically spend about 100,000 years in this late life phase, so statistically it's unlikely to happen during our brief human lifespans. It's kind of a shame, though. If Betelgeuse did go supernova, its distance, 650 light-years away, would be perfect. Far enough to be safe, but close enough for incredible scientific study. We'd get an amazing light show, too. At its peak, it could outshine the full moon. Or it might just vanish, leaving behind a black hole, which would also be an incredible discovery. Massive stars like Betelgeuse are fascinating. They're rare giants that probably never form planets, let alone life. Yet they're deeply connected to us. Many heavy elements in your body, phosphorus, potassium, oxygen, were forged in stars like this. When these stars died in violent explosions, they scattered these enriched materials across the galaxy. That stellar debris, still rich in hydrogen, formed new generations of smaller stars and eventually planets packed with life-essential elements. The same atoms inside you right now were once part of a massive star's core. You're literally made of stardust. Watching Betelgeuse is like seeing our own origins. These stars destroy themselves in almost sacrificial explosions, creating the conditions for complex chemistry and life to eventually emerge, rising like a phoenix from the cosmic ashes.